Thank you so much for giving me the opportunity. I'm Imtiaz Mahmud with the SDM group. So here I'm going to present our recent work on decentralized HPC facilities. So this is a simulator that we have developed. The name of it is DISTRI, the development and integration of simulation tools for resilient infrastructure. And the way it works, or the thing we actually emphasizing is on the decentralized computation. So right now, if we imagine the world it is going on, that we have separate computational facilities, they're totally separated from each other. There's when a user submits a job, it remains inside that facility. For example, if a user submits a job in the LBL, it remains inside the LBL. It does not share it with other facility. Whereas this results in a significant overutilization or underutilization, and also it wastes the resources, and it also creates a security vulnerability, because if a server goes down, it goes down with all the jobs. So that's where a decentralized and distributed multi-facility computational system comes. So our vision is a fully decentralized computational facility. So the facilities will be distributed all over the globe, but still a user can submit a job anywhere, but it will be computed in its best location. So the facilities would itself decide which facility will do the job. So we are looking at the geographically distributed facilities acting as a unified system, distributed and decentralized and seamless and efficient system. There is no centralized control. So all the things will be distributed, decentralized, and we are thinking of multi-architecture agent-based system. To envision it more from in depth, we are actually thinking it as a multiple layer system, where in the lower layer there are different computational facilities like LBL, ORNL, and in each facility, each resource, we are considering them as an agent. So the resources represented by agents, they form a agent network in the facility, and from them they select a leader. That leader becomes a part of the global chain that forms a dynamic job pool. So in that global chain, whenever a user wants to submit a job, it submits a job in that global chain. That is a dynamic job pool. And from there, the job flow starts. The jobs as the agents themselves inside that dynamic job pool, they have some consensus algorithm, and they decide that which computational facility will take over the job. And then that computational facility takes over the job and does the job, executes the job. And it is actually updated between the dynamic job pool. And if a job fails, the dynamic job pool is informed, then any other computational facility can take over. And we're also looking forward so that even a job can be executed in multiple computational facilities. So that is also our future envision. So that's what actually we are envisioning the future decentralized computational facility. And to achieve that, the key component will be a simulator that will give us the opportunity to test multiple systems with multiple algorithms that we are going to develop. So for that, in this DISTRI architecture, we have first there is the multi-facility system, where there is a dynamic job pool. As I mentioned before, the jobs are residing there. Then there is a computational facility where each computational facility can act as act on its own. The computational facilities are itself connected by the edge routers in the simulator, and they also have a control network that gives the computational facilities to communicate with each other with control messages that will be short burst of messages sent immediately. And inside a single facility, there are also some components like the resource manager, the agent that is contributing to the dynamic job pool as a leader. We also have the data transfer node in the facility. We have the resource agent, that is those agents that are the job. And we have the routers connecting the agents. We have a data plane where the data are there connecting the details and the resources. And we also have a control plane where control messages are sent. So all these facilities are there in this simulator. This simulator also gives you some network components, like you can use different kind of TCP congestion control algorithms like Reno, Cubic, HTCP. These are the end-to-end communication protocols that enables data transfer. So you can test different network protocols, and also it have different routing algorithms like FQ, FIFO. These are the queuing algorithm inside the router. So you are also getting those to test different kind of scenarios. And then we are going to an example where I will show you that how it can work. But to give just to in a gist, you can do a lot of things. You can change any parameter, and you can use different kind of algorithms and test the result. So for the simulation, for example, here we are simulating it for 200 seconds. You can change the router's speed, the routing number of packets. You can also change the edge router and the inside router both. And you can also have different kind of categories of job. So you can define like computational heavy job, this one, computational data heavy job, and some jobs are like computational both data heavy. So different kind of job you can decide and you can set. Then the simulator will generate those kinds of job and simulate between the commercial facilities. So, and then finally you will get an overall result where it is showing you the turnaround time for the jobs to be completed, and you can see for different kind of AQML, different type of algorithms like we have Reno, Cubic, HTTP as a constituent algorithms, and also have some AQML algorithms like FIFO, FQ. So these algorithms, by setting these parameters, you can also compare the performance of those algorithms in respect to and how they're impacting the overall performance in terms of turnaround time. And then you can go deeper. For example, in this example, if you see that FIFO is always performing better in compared to FQ. So why that is happening? We can go deeper. So these are all auto-generated images. So here you can see the buffer size inside the routers, and you can see the number of packets that those were retransmitted. So you can see that FIFO had very less amount of retransmissions compared to FQ. So why is that? You can go more deeper. You can see the each routers queuing space, that how much packets were queued and what the queue overshooted or not. So you can see that the most of the time the queues are overshooted. So all the packets were there, so they are over. That's why the packets are dropped. So you can in this way you can go more deeper and see what is happening inside a specific facility or inside the network also. And then DISTRI also simulates the faults. It simulates the faults like disruption in the resources. For example, a resource can go down, so it can simulate that, and it can also simulate the file system errors. So when those errors occurs, so it simply restarts that resource and it reallocates that job to some other agent. So simply those jobs are actually, those resources are actually those jobs associated to those resources are released. They are available to the global job pool. That any other agent can pick up the job. And for that, we are also implemented a heartbeat message that the resource always sends back to the agent leader. That enables it to communicate, ensure that whole agent is alive or not. And that makes it possible to track the agent without a centralized control. So in conclusion, DISTRI gives a simulator that can simulate both single facility and multi-facility, and leads us to a decentralized, distributed, and resilient multi-facility system. It supports simulating computational facilities, and it simulates also the agent-based scheduling, TCP layers with multiple congestion control algorithms, and routers with multiple AQML algorithms. So these are just the beginning. It also simulates like the network congestion, cross-facility data transfer, and resource failures. However, in future, we are also envisioning it to expand much further, where we can actually simulate the network layer protocols like how the packets are transferred between the routers. So that is our goal also one. And we are also trying to include the LLMs inside the simulation, so that there should be some LLM agents that can optimize the network and optimize the data transfer or optimize the job allocation. So that's all for today's presentation. All the resources are there. You can go and get the access to the resources.